Hello everyone, and welcome to today's webinar on the French experience in advancing nitrous oxide quantification towards mitigation. My name is Erika Varga, and I will be your moderator today. Before we get started, I would like to share a few housekeeping rules. I have the control. Yes. So one of the most frequently asked questions is whether this webinar will be recorded and the slides will be available after the session. The answer to that is yes. Following the webinar, the sessions will be published on the IWA website as an on-demand webinar and will be also available on Connect Plus. Please note that the speakers are responsible for the content of their presentations, and the views expressed do not necessarily represent those of IWA. As you may have noticed, the participant microphones and cameras are turned off. We encourage you to use the chat for discussion and the networking, and the Q&A box to submit questions for our panelists throughout the session. We will discuss that in the panel discussion at the end. Today's program focuses on the work of the ASTE Greenhouse Gas Emissions Working Group, specifically on nitrous oxide emission factors. Following this short introduction, we will begin with Alan Filali, who will help to set the scene and introduce a broader context. Then Romain Lemaire will share practical experience and insights on N₂O emissions from wastewater treatment processes. And after that, Alan will return and discuss additional emission sources, including the effluents in receiving water and sludge treatment. Finally, Mathieu Sperandio will present with the conclusions and perspectives before we move into the panel discussion. Before we begin the presentations, I'd also like to say a few words about the Climate Smart Utility Initiative greenhouse gas emissions subgroup. As many of you know, the Climate Smart Utilities focuses on the climate adaptation, mitigation, and leadership. The mitigation subgroup on greenhouse gas emission monitoring has been active since 2021, with a focus on having a shared tool and approach for greenhouse gas monitoring. This community of practice, our activities include organizing webinars such as today's session, regular calls for practitioners, and contributions to publications, including white papers and technical reports. We will also pick up our monthly calls in June after a little bit of a hiatus. If you would like to join this little active subgroup, then please scan the QR code here on the screen and be informed about upcoming activities. I will also share the link later in the chat. And now, without further ado, it is my pleasure to welcome our first speaker, Alan Filali. She's a research scientist in environmental bioprocesses in INRA, in the PROS research unit. She holds a PhD in process and environmental engineering from the University of Toulouse. She completed a postdoctoral fellowship at IRSTEA, which is now INRA, from 2012 and 2013, and has been research scientist there since then. Her main topics include nutrient removal and recovery, as well as energy optimization. Her work spans multiple scales, from laboratory to full-scale system, combining experimental approaches with modeling. Alan, welcome. The floor is yours.
Well, thank you, Erika, for the introduction, and thanks as well to IWA and Climate Smart Utilities for organizing this webinar. Hello, everyone, and thanks for joining us today. It's really nice to see so many of you connected. So today we're going to talk about nitrous oxide, N₂O, which has become a major topic for the wastewater sector in many countries, including France. And we'd like to share with you what has been done on this topic within our French group. Only 3 of us are presenting today, but many more people contributed to this work. So in this first part, I'll briefly introduce the group behind this initiative, our objectives, and the overall methodology we followed. Okay. Okay. So just to briefly introduce the context, this N₂O initiative was developed within ASTE, which is a non-profit association and the IWA representative in France. ASTE brings together around 4,000 professionals from water and waste sectors, and it hosts several working groups, and one of the oldest and still very active today is the Greenhouse Gas Working Group. So this group has several missions, and one of them is to provide and update the methodological guide for greenhouse gas assessment for water and wastewater services. And this guide was initially developed to support greenhouse gas reporting that has been mandatory in France since 2012 for public and private companies and for large local authorities. And within this large group, our N₂O subgroup focuses specifically on improving N₂O quantification for the French wastewater sector. How the adventure started, things really accelerated with the 2019 update of the IPCC guidelines. This update increased the default N₂O emission factor for biological nitrogen processes in wastewater treatment plants by more than 40 compared with the 2006 guidelines. And this new emission factor completely changed the greenhouse gas footprint of wastewater treatment plants. So you can see it here with this example from a French plant. With the 2006 emission factor, N₂O, here represented in neon green, is already a significant contributor, as you can see it, but still lower than electricity consumptions, chemicals, or transport. But with the 2019 factor, well, I think the picture speaks for itself. Clearly, N₂O dominates the carbon footprint to the point that reducing emissions from other sources becomes irrelevant from a climate perspective. And this shows you how sensitive the carbon footprint of wastewater treatment plants is to N₂O emission factor, especially in France, because we have an electricity mix that is low in carbon because of nuclear energy production. So following the 2019 updates, it became very important for us to revisit N₂O emission factors and adapt them to the French wastewater context in line with IPCC recommendations. So we can change. Thanks. Let's move now to the objectives. Of course, the first objective was to refine and adapt N₂O emission factors to French wastewater treatment practices and technologies. But beyond updating numbers, we also wanted to better understand the variability of the emission factors. So, for example, analyze why some treatment processes have higher or lower emission factor ranges than others, and how process design and operating conditions can influence N₂O emission levels. Knowledge sharing was also a key part of the work because N₂O emissions are a complex topic involving, as you know, multiple producing pathways and many interacting factors. So for us, it was important that practitioners grasp this complexity and better understand the uncertainty associated with generic emission factors. Another important objective was to identify the main knowledge gaps and the area where additional measurements are still needed. At the end, altogether, this deeper understanding and sharing knowledge is essential if we want to support future mitigation initiatives on a more informed basis. Okay, so regarding the scope of the work, we looked at the main sources of N₂O emissions. As you know, a large part of N₂O production is in fact linked to biological nitrogen conversion processes, namely nitrification and denitrification, that happen during wastewater and reject water treatment, after the discharge of treated effluent in the receiving water bodies, and also during treatment, sludge treatment and management. The main exception here is in fact sludge incineration, where N₂O formation is linked to combustion process and not to microbial pathways. So to address these different topics, we organized the work into 3 groups, each bringing specific expertise on these emission sources. Well, it looks I have the control now. And here you can see how the contributors were distributed between the different emission sources. So the composition of the group evolved over time. So I think we started working on the data around 2020. And obviously the composition evolved depending on the topics we were working on. But this slide gives you the overall picture. As you can see here, and from the large number of gray dots, the large part of the work focused, in fact, on wastewater treatment. This was the core group, mainly because this is where most of the data were available. The contributors included 3 academic institutions, INRAE, CNRS, and INSET Toulouse, together with 2 companies, Veolia and Suez, and 1 large utility, SIAP, that so SIAP serves around 9 million people in the Paris region. And beyond the people shown here, we also received broader inputs from utilities and practitioners through the ASTE Greenhouse Gas Working Group. Regarding the methodology, the approach depended mainly on the level of data available. So when French monitoring data were available, which was the case for wastewater treatment and receiving water bodies, the first step was to review the measurement protocols and select the data sets considered sufficiently reliable. Then we analyzed the emission factors and their distribution across process design parameters, environmental and process operating conditions. For wastewater treatment, this work was complemented by an extensive literature review to benchmark the French data sets against international data. And for sludge management, so this is path B, for which we had, in fact, limited national data, the work relied more on literature review and expert discussion to evaluate if the data were or not representative of French practices. This work resulted in 3 technical fact sheets. We wanted these documents to remain practical and directly usable by practitioners, so they were written in French. Each fact sheet presents the scientific background, the refined emission factors, when it was, of course, possible to produce them, and the associated uncertainties. So these fact sheets will now be briefly presented, together with the main perspective of future work. And with that, I'll hand over to Romain, who will present the main results for wastewater treatment.
Thank you, Ellen, for this introduction. First, I would like to welcome Romain to share the practical experience and insights on the nitrous oxide emissions from wastewater treatment plants, as Alan mentioned. Roman is a biological and process engineer. He obtained his PhD in 2007 from the Advanced Water Management Center of the University of Queensland in Australia. He worked at the Veolia Water Research Center in Paris for 3 years as a research project manager on biological nutrient removal and particularly advanced nitrogen removal processes such as Anamox, nitrogen and biofilm processes, but also N₂O emissions. He joined the Veolia Technical Department in 2011 as wastewater expert from the development and industrialization of new biological processes. He is in charge of process validation and technical support for design, build, and operation projects in municipal and industrial facilities. Welcome, Roman.
Thank you, Erika. Hi, everyone. So yeah, I'm gonna taking you now through the wastewater part of N₂O emission from France. So this first pillar that Alain presented just before. I'm just gonna check if I have the control or not. So as Alain was saying, we try to apply to the specificity of the French wastewater configuration we have. So if we look at what happened in France, of the number of plants, the type of technology we have, and the load treated by those technology, you have this kind of mapping. So in terms of plant number, activated sludge is clearly number one, like in most of the countries around the world. And we see that the extensive solution, like a constructed wetland or lagoons, are also quite numerous in number, but for rural or small plants. We do have biological aerated filter and other technology, but in few number. But then if we look on the right hand, the load treated by each of these processes, activated sludge stay number one, but the BAF becomes number two in France. We have a lot of very large BAF plant historically in France on urban area when the footprint is a driver or a limitation. And therefore, we decided within the group to focus on those two main processes to assess the N₂O emission factor and to try to see if there is a difference between those two technology. Next slide, please, Afia. Looking at the French data set, we all have academic utilities or private sector. The idea of this ASTI group is to share what we have, not really published internationally, but in internal data. And as Alain was saying, we had a screening of was it the campaign, N₂O campaign was long enough, done in the same way, so we can compare an apple and apple in this different N₂O campaign that everyone shared with the group. So at the end, we selected 8 activated sludge plants and 6 biological aerated filter plants when we have reliable and long enough N₂O emission measurements, so we could express then and calculate the emission factor of those plants. Looking at the activated sludge plant, they all NDN configuration, so nitrification and denatrification, with full nitrification. So it's important to mention that in all of those plants. We have the load. So we found that the load was a criteria I wanted to see how loaded the plant was compared to the design capacity. In France, the average load of the plant is around 50%. So we have a lot of extra capacity, I will say, in most of the plant, or they're not loaded to the design load. So in those 8 plants, we are ranging between very low loaded plant, not even 10% or 10% of the design capacity, to somewhere around 80%. So it gives you a big spectrum of applied load to those plants. And the volumetric load, it's low loaded or extended aeration type of plant in France a lot. So that's the load we had for nitrogen. Keep in mind as well that most of those configurations in France, they are oxidation ditch with intermittent aeration. We have very few large plug flow or MED plant in France by, yeah, that's the way it is in France. For the biological aerated filter, we have different configuration, but all of them with at least nitrification. We want to look at N₂O emission, so nitrogen removal needs to be involved. You see the configuration, they can be CN. So CN, you have to understand that it's nitrification. So we remove carbon and we nitrify in the same biofilter. We can have NDN configuration. So there is COD removal happening upstream, either with another bath or an activate sludge or something else. And the bath is only doing nitrogen removal with some denitrification with recirculation, for example. And we had also secondary nitrification, what we call, when we only nitrify in those filters, and the carbon removal is done upstream, but there is no denitrification happening in the filter, no recirculation. So different configuration possible. You see that the load apply is much higher because they are modular by design. They're modular with different cells. So close to the design capacity, most of the plant, and with a much higher volumetric load because they are very compact, and that's the way those bath systems are designed. Next slide, please. So if we look now at approach, that's one of the big, I would say, difference of what the IPCC has been using. We all know that it's generic nitrification is, as Alem was presenting, is generating the N₂O. It's the main way to generate the N₂O in the system, even if denitrification can be involved as well. But when we aerate, that's where we strip the N₂O. So that nitrification stage is key to link to the emission factor. So the IPCC approach, you all know, it's per TKN in the influent, or it's the emission factor is expressed per TN or per nitrogen in influent, which for domestic, it's clearly TKN. In our approach, we found that this methodology was a bit difficult to fully compare apple and apple on the specificity of the plant. So we decided to move to TKN remove. So at least the emission factor is linked to the amount of nitrogen which is removed in the plant, and focusing on TKN more than TN, because we found that nitrification, before denitrification, you need to nitrify, and it was easier and more comparable to use TKN remove. So that was our approach, and I will show you why in the next slide and try to explain a bit better this approach. So here you have 3 design case scenario, and just to show you the difference, if we use TKN from the influent as the emission factor, like the IPCC is saying, or TN remove or TKN remove, which is our approach in the working group. So if we start from the general plant, let's say we have 100 kilo of TKN coming in to the plant. Okay, that's this hypothesis. If we look on the left part, the left example, this plant is emitting 1 kilo of N₂O per day. So let's say 1% of the inlet load. So it's a fully, case 1, it's a fully nitrifying and denitrifying plant. You see that we are removing 95% of the TKN, and we're doing 80% TN removal. In that case, we see the 3 different approach, the IPCC, or if we look at TN remove, or if we look at TKN remove, you will see that the emission factor will be really close to each other because we have a almost full nitrogen removal. Few differences because TN versus TKN remove is not exactly the same in that example, but we see that it's comparable in that case. If we move to the middle one, which is now a case when we do carbon removal and only nitrification, no denitrification, which happen in the UK a lot or in some part of the world, that is the reality. In that case, we do remove TKN, so 95 kilo per day is removed of TKN is removed, so 95% TKN removal, but there is very little denitrification. 10%, mostly assimilation and so on, or a bit of denitrification, but very limited. In that case, we see that the approach of IPCC and our approach, we still give similar emission factor because most of the TKN is removed. So inlet or remove is similar. But if we use the TN remove approach, which some people are saying, oh, it's nice to use TN remove, but we see that there is a problem for plants who don't denitrify. The emission factor will become absolutely berserk and not realistic to the mechanism behind the N₂O emission. And the last one is if you have carbon removal only, so let's say your plant doesn't nitrify and don't denitrify, you have no N₂O emission or very little. In that case, it's only assimilation for nitrogen removal. Obviously, in that situation, the IPCC way of by TKN from the inlet doesn't make any sense because you are not removing nitrogen. So we see that the approach in those three scenarios is the most consistent to link emission factor to TKN remove. Next slide, please. So with that said, now looking at the data we analyzed in our study. So at the top, you have everything coming from reject water, so anaerobic centrate, anaerobic sludge digestion centrate. When we have biological removal on those flux, this is coming from literature, not from our own French data. We didn't have data to share at that stage. And we have the partial nitrification doing just nitrification on the centrate. And you have also the PNS, or partial nitrification, and the anamox system, which is removing all the nitrogen. And we see that looking at the literature, we have a bit of a discrepancy between the two. And we see that the anamox system will provide a bit lower emission. So the emission is in log scale at the bottom, emission factor. So be careful of that. But we think there is a clear difference between something which is just nitrifying on those centrate or something which is nitrifying and removing nitrate, for example, with the anamox. So there is a clear advantage to get the anamox working and sucking away the nitrate from the system, being able to lower a bit the emission factor. So this is published data that we reviewed. The bottom of the graph is from wastewater, from the main water line. And here we make a difference between the BAF, which is only coming from our data from France, compared to the activated sludge, which is the bottom one in purple, which is activated sludge from the 8 plants we monitored, and also some from the literature to have a bigger pool of data to compare with. And we see clearly that the BAF emission factor are significantly higher than activated sludge. And we have a much broader and wider scope for activated sludge. If we look at the literature review and the publication we can see, and even with our data, we see that the distribution of emission are much wider in that case. But there is a clear difference between the BAF and the activated sludge. So the intensity of nitrification, doing nitrification like a Ferrari, a BAF, you have to imagine that it's really high loaded for nitrification. Activated sludge, more extended system. We see a clear difference between the two, and it doesn't make so much sense to apply a single emission factor for those two systems. Next slide, please, Afia. So focusing now on activated sludge only with NDN configuration, so full nitrogen removal. Now we distinguish between the survey we did from all the literature review, which got meaningful data for N₂O emission, versus the French data at the bottom. And we see when we split the two, we do see a clear difference as well between the French data, which is significantly lower than the average of what is published internationally. This is mostly due when we analyze the specificity of those French activated sludge plant. They are very low, I told you, low loaded plant compared to their design capacity. The FM ratio is relatively low. We've got extended aeration with long sludge edge. And they are also in this configuration of a fully mixed plant, so oxidation ditch with intermittent aeration. That's the majority of the configuration. So all that makes some specificity, which could explain why we have lower emission, it seems, compared to what has been published internationally for activated sludge. Next slide, please. And we also analyzed that data looking at different study or different published study. You see in gray the circle. When we look at the emission factor, so we express here per TKN inlet because all of those data sometime were using that emission factor and not per TKN remove. So we tried to and we didn't have access to the TKN in the outlet, so we couldn't calculate the TKN remove. So in this, we plot the emission factor compared to the amount of nitrogen removal and the denitrification. They're all fully nitrifying, but then you see the TN removal at the bottom is not always the same. On the right, you have all the fully denitrification plan, and on the left, the one denitrified with less denitrification. And the diamond plot are the French data we have. What we see clearly is the denitrification. The more you denitrify in your plant, the lower the emission is because it is a clear sink to N₂O. N₂O can be denitrified. And we see that our French plants are usually doing full denitrification, which explain as well, compared to the rest of the literature we can find, why the emission is significantly lower for the French reference we've got. Last slide. So looking now at the result of what we propose for France as default, I will say, emission factor per configuration. We have one for activated sludge and one for BAF, and you can see they're really different. We look at the mean emission for emission factor for activated sludge of 0.06%, much lower than the IPCC, and relatively lower than some of the literature linked to the specificity of the French configuration of activated sludge. The confidence interval is quite large, but the variability is high as well in our data set, okay? Like if we look at what is published internationally on activated sludge. For biofilter, it's much higher, 1.6% or 1.65 to be for the mean for 8 BAF system. But we have a confidence interval which is much narrower and lower variability as well. Okay, so this clearly shows that's the main finding we found in our study, and that's what we recommend to use when utilities are doing their carbon emission from the plant. In France, we propose to use those numbers instead of the IPCC. So there is some thing to take into consideration for activated sludge, like it is SBR, so we didn't have any SBR, so this batch-wise can change a bit also the dynamic of emission. Is there partial nitrification? Is it carbon-only treatment with some nitrification happening just in summer? Sometimes you're in that gray zone. That could increase as well the emission factor. The plug flow effect, I told you we are more dealing with fully mixed plant and not a plug flow system in France. All that could influence the emission factor again. And the operating condition as well, the fluctuation of the incoming load, for example, when the reject water is injected to the head of the plant, is it only when dewatering is happening, or do you have a buffer tank or those kind of stuff? Alkalinity limitation or pH as well have an influence. Nitrite accumulation as well. So all that is also something influencing the system. So with that, I think so thanks for your attention. I want to special thanks to Noura, a trainee from ASTE, who did a lot for the literature review, because it's a lot of data available and it's a lot of work to try to see what we can use, what doesn't, the methodology involved is not fully in line with the others, so we excluded some of that. So big thanks to Noura for that, and to all the team who contributed to that to that work, and now it's available on the ASTE website, and will be translated in English sooner or later. So for those of you who don't read French, thanks.
Thank you, Roman. Thank you very much. It was a very insightful presentation, and I'm curious that in addition to the things on the process design and operating conditions that you mentioned, how the new Urban Wastewater Treatment Directive, the implementation of the new Urban Wastewater Treatment Directive will provide you more data or more insight with the changing effluent limits. Just before we move on, like a quick reminder, if the international calculations that you showed in the comparison was based on the removed or the influent TKN, so the emission factor of in your comparisons, that can you remind real quick?
Yeah, so we try when we could for international publication, when we could, or literature survey, when we could get the TKN remove, we then apply TKN remove. In some of the case, we couldn't get that from the publication. We didn't have the data available. So when it's a fully nitrifying plant doing full nitrification, there is no so much difference between TKN in or TKN remove. In that case, we could compare, and that was the case study I show you, we could compare, TKN from emission by TKN inlet or TKN remove. They're very close to each other when the nitrification is complete. So we try, so sometime to compare, we had to play a bit with that, but the data is not always available, TKN remove. And we understand that providing this approach might keep a bit more complicated because you need to know TKN in and the TKN out. But if you are just ammonia in, it's relatively easy on municipal wastewater from ammonia out to know what is your TKN out. You can easily estimate that. But clearly we had to play a bit, but we try to be consistent. So in the graph I show you, sometimes it was TN remove, sometimes TKN remove, sometimes TKN in, but each time, because we could apply, because the plant was fully nitrifying or fully denatrifying, and we could use one or the other, if it answers your question. But we've been very careful in making sure we're picking the right way of expressing the emission factor.
All right, thank you very much. I see that some new questions are coming up. Thank you from the audience. We will come back to those at the end in the panel discussions. Now we will move on to our next presentation with Alam, who will discuss additional emission sources beyond the treatment processes itself.
Okay, so it's me again. All right, let's move on the other emission sources we considered in our work. Okay, it's working. Starting with receiving waters. So before discussing emission factors, before discussing emission factors themselves, it seems important to have in mind that wastewater treatment plants are not the only anthropogenic sources of nitrogen in surface waters. Agriculture, livestock, and groundwater sediment interactions also contribute to nitrogen inputs in surface waters. And in that case, isolating the specific impact of wastewater treatment plants is quite challenging. So in the map you see here, you have the nitrogen loads discharged from large wastewater treatment plants into surface waters. And the larger the cycle, the orange cycle, the larger the load. So what you can see here is that the Paris region clearly is a major hotspot, followed by other large cities, including some of them discharging into coastal waters. So now, why am I talking about nitrogen loadings? Well, because a general observation, and here we can do the parallel with wastewater treatment plants, a general observation here is that higher nitrogen concentrations in receiving waters tend to lead to higher N₂O emission factors. So in our work, we based the work on Paris region data. And from here, we can conclude that Paris regions appears relevant to do this work because these conditions, at least theoretically, would be less likely to lead to an underestimation of the emission factor. So here we zoom in on the Seine basin. The sampling points are grouped into 3 zones across the samplings basin following the water flow. Zones A and B are located upstream of the Paris wastewater treatment plants, and this zone was used as reference areas, reference data. And C is downstream from Paris area towards the estuary. Each red dot point that you can see here in the image corresponds to a sampling point monitored over several years and across different seasons. For the emission factor revision, we used only the 21 data points from zone C. And why we used only this zone? It's because in this downstream area, we expect the contribution of wastewater treatment plants to N₂O emissions to become much more significant compared to the other nitrogen sources present in the basin, as I explained earlier, like agriculture, livestock, etc. And the data that we used come from monitoring campaigns published by Josette Garnier and colleagues. Oh, sorry. Before showing you the results, I think it's useful to briefly look at how the default IPCC emission factors for receiving waters were established. So the IPCC database combines studies from different continents and different surface waters, in which emission factors were determined using different approaches, mainly three approaches. So the first method is based on laboratory studies performed on microbial cultures or soil incubations. And these studies are really useful to investigate mechanisms involved, but they usually give higher emission factors than field measurements. And something that has also been observed for wastewater treatment plants. The second approach is based on field emissions measurements performed either using floating chambers, like the ones we use in wastewater treatment plants, or by estimating N₂O emissions from dissolved concentration through gas-liquid mass transfer models. And then these emissions are normalized by the nitrogen inputs into the receiving water to derive the emission factor. This works at the scale of a river section, but when extrapolating it to an entire river basin, it quickly becomes much more complex because it requires some modeling work and to perform a full nitrogen budget. So it's not that applied in literature. The third approach, and this is actually the one we used, is the concentration ratio approach. In this case, the emission factor is estimated from the ratio between dissolved supersaturated N₂O and nitrate concentrations. Why nitrate? Because it's the dominant form of nitrogen in receiving waters. And supersaturated N₂O simply means that is a fraction of dissolved N₂O above atmospheric equilibrium. So this part reflects in water N₂O production. So this third approach is the most commonly used approach in the literature, and I guess because it's much simpler and requires only concentration measurements. Once the emission factor is derived, indirect N₂O emissions from wastewater treatment plants related to the effluent discharge are calculated with the IPCC framework using total nitrogen in the effluent. Why here we consider total nitrogen and not TKN as in wastewater treatment plants? Because in surface waters, clearly denitrification takes a much bigger role, and both nitrification and denitrification are expected to contribute to N₂O production. Oops. Okay, never mind. So now moving to the results, the graphs on the left show the different water quality parameters and the corresponding emission factors across the three zones. And what clearly appears downstream of Paris is the impact of wastewater treatment plants discharges. You can see here that nitrogen concentrations, ammonia, nitrite, nitrate, increase, while dissolved oxygen decreases, which is a sign of intense microbial activity due to this nitrogen loading. And also, we can see that higher N₂O emission factors are increasing. Based on Zone C data, we then identified a negative relationship between dissolved oxygen concentration and N₂O emission factors. So following the IPCC approach, we used a 3 milligram dissolved oxygen threshold to separate well-oxygenated from oxygen-depleted waters, which led us to produce two emission factors that you see here in the screen. And although our values are lower than the default IPCC factors, which is something we can discuss, the overall trend remains consistent. We see here that oxygen-depleted and nitrogen-rich waters are associated with higher N₂O emission factors. So here we can draw a parallel with wastewater treatment plants. Okay. Oh, sorry. All right. And a few limitations and perspective before moving on. First, these emission factors that I showed you were derived from freshwater measurements in rivers. But as you know, and as you have seen in the map that I showed you, several large French cities discharge their treated effluents to estuaries or coastal waters. And for now, we apply the same factor regardless. This is clearly a simplification and a point future work should refine. Second, the emission factor presented here applies to treated effluent, okay? Wet weather overflows, which bypass treatment plants, or at least some treatment steps, bypass these effluents to the receiving waters. And well, this represents as well a separate emission pathway that I think deserves its own assessment in future work. Okay, without further ado, let's move now to sludge management. Here we mainly focused on composting, land spreading, and incineration, which are the main end-of-life routes for sewage sludge in France. Unlike for receiving waters, I will not present specific emission factors here, because in fact the work is still under progress, and the emission factors we are building from new field measurements will be refined in the incoming period. Mathieu will talk about it. So rather than showing you numbers that may change in the near future, I prefer to share with you the main conclusions from the literature review we did. Okay. One of the main reasons why emission factors for sludge management still come with high uncertainties is that N₂O production depends on many interacting factors and also on conditions that are often less controlled than in conventional wastewater treatment processes. And that's what this slide is trying to illustrate. So at the center are the nitrogen conversion processes. So for composting and land spreading, N₂O is produced during nitrification and denitrification. Other pathways like ammonia volatilization or nitrate leaching won't produce N₂O directly, but still will influence the amount and the form of nitrogen available in the system, and therefore indirectly affect N₂O emissions. And in this system, these processes takes a high share on nitrogen conversion. Incineration is different because N₂O is formed through thermal reactions at high temperature. And here also the mechanisms involved are quite complex. Around these processes, two major groups of factors control N₂O emissions. The first is the characteristics of the input material, meaning the characteristics of the sludge itself. And in the case of composting, also the co-substrates that are usually mixed with the sludge. And when I'm talking about characteristics, I'm talking about carbon to N ratio, the moisture content, the nitrogen content of the sludge, etc. The second group of influencing parameters is related to the process technology itself. There are differences when you work with one technology versus another one, like open composters or closed composters. It's related as well to management practices and to the surrounding environmental conditions. So all of this contributes to the very large dispersion observed in the emission factor data, with sometimes when you read papers, contradictory findings that makes drawing clear conclusions sometimes quite challenging. And despite the complexity I have just talked about, in fact, our understanding of N₂O production mechanisms has clearly improved over the last years. So thanks to advances in isotope tracing methods or molecular biology tool, the biological pathways involved in N₂O production are now much less of a black box. We also have more and more studies looking at the influence of operating conditions and management practices. So a good example here is composting, where the role of different co-substrates that are added to the sludge before composting. So now we can see that several co-substrates coming especially from agricultural residues are increasingly investigated and in line with circularity principles. That said, most of these advances comes in fact from small-scale studies, either lab scale or pilot scale. What is striking is that sewage sludge remains largely underrepresented in N₂O studies when compared with other organic residues, such as manure or organic fraction of municipal solid waste. And this is especially true for composting and lead spreading, where reliable and representative field data are still lacking. One reason is that these open systems have really strong spatial heterogeneities, in fact, much stronger than in wastewater treatment plant processes. And the treatment process also here occurs over much longer time scales. So in wastewater treatment plants, treatments typically occur over a few hours, that is fixed by the hydraulic retention time. But in composting or land spreading, this treatment takes place over longer times, several weeks to months. So obtaining a reliable and representative emission data requires, in fact, long field monitoring. And this probably also explains why more data are available for sludge incineration, as it is a channeled source with a single emission point. So the measurement is clearly much easier. Oops. Okay, last slide. Overall, we identify three main levels of emission factor description. The first one is the IPCC approach, which relies on generic emission factors. And for composting and land spreading, groups sewage sludge together with other organic residues, despite very different composition and properties. A second, more refined level is provided by dedicated tools. So here I show you two of them. The BEAM, which is the Biosolid Emissions Assessment Model, originally developed in Canada, or LCA tools like Gestabou in France. These tools or approaches compile literature data and try to distribute emission factors across to some key operating parameters. So for example, here for incineration, we know that N₂O emissions depend on the sludge nitrogen content and also on furnace temperature. So clearly we can use this correlation to better evaluate N₂O emissions. And finally, what we see as the longer term goal is to move towards sludge quality informed emission factors, better accounting for sludge biochemical properties. So today we have some evidence that some data suggesting that using different types of sludge leads to different N₂O emission levels. So for example, stabilized sludge, like the ones that have been composted or dried, tend to produce lower N₂O emissions than raw or liquid sludge. And this distinction between sludge types, I think, will become essential if we want to properly compare and guide sludge management routes from a climate perspective. Okay, and with that, I'd like to thank all contributors to the two sources, sewage and sludge management. Thank you.
Thank you very much, Alam. It was very interesting, and yeah, there are a lot of uncertainties, especially whether we consider these as point emission source or diffused, as you mentioned. We have quite a few questions about measurement and monitoring related topics, but I think that it also applies to Roman's presentation and yours, so we will come back to those later if you don't mind. We are already a little bit behind in time. So if it's okay with you, we will move on to the next presentation, which is by Mathieu Sperandio, who will share some conclusions and perspectives on these kinds of work of the working group. Mathieu is a professor at INSA Toulouse, and the deputy director of the Toulouse Biotechnology Institute and a member of the management committee of the Nutrient Removal and Recovery IWA group. After a PhD in chemical engineering, postdoctoral period in AWMC in the Queensland University, he obtained a position in 2001 at INSA and became a professor in 2009. He was invited professor in Montreal Polytechnic. He has supervised 30 PhDs. If you can believe it, 2 of those are right here in this panel. Authored 85 scientific publications, 3 books, and 3 patents. In the last 10 years, his work was dedicated to nitrous oxide emissions from biological wastewater treatment, nitrogen and phosphorus recovery technologies, and source separation. Mathieu, thank you for joining us, and the floor is yours.
Okay, thank you very much, Erika. Thank you all to invite us for this presentation. I will try to be quick because I have seen also a lot of questions in the Q&A panel. So let me just conclude this presentation by showing you a few take-home messages and also some perspectives about the mitigation approach that we can try to develop. So first, well, the main message that you need to learn today is the fact that we had quite a significant amount of campaigns which have been done on the French plants. That activated sludge systems definitively showed relatively low emission factors for N₂O. And as Romain said, it's probably due to the fact that the loaded are generally very low in this activated sludge in France. I've seen some question about how did we measure this emission factor. So let me say that Alain can give you more information, but most of the time it comes from weekly campaigns at different moments in the year. And these campaigns have been done also on nitrifying biological aerated filters, and we have seen that relatively high emission factor. So this helps us now to refine the emission factor calculation for the French situation. And obviously we have some dispersion, but relatively, if you compare this dispersion to the level of the emission factors, we see that it's not that significant in the fact that for the BAF, as Romain said, the emission factors are relatively comparable. And for the activated sludge, even if we have dispersion, it's for most of them, we have low emission factors. So this can help us to support actions and to develop some strategies for mitigation. And you can compare this result to other international initiatives with different countries. Obviously, we have such kind of variation of emission factors, but clearly we are in the range of variations that which is observed for different systems in Europe or in USA. But we have that specificity of low emission factor measured for activated sludge and high emission factor for BAF. So naturally, in the last decade, we did specific works on biological aerated filters, and I would like to show you a few examples of that result. The first thing is, if you see these figures, this gives you an idea of the emission factors as a function of the applied load in BAF. And the first message is that the highest emission factors are obtained when the system is operated at relatively high load. On the left side, it corresponds to an average daily emission for real experimental monitoring campaign on different real BAF. And on the right side, it's obtained with modeling during the PhD of Justine Fiat with a tool that we have calibrated on the real data information. And you can see that experimental data and modeling results give relatively similar information. There is an increase of the emission factor from about 1% for the lowest load from 0.5 kilogram of nitrogen per cubic meter per day. And this emission factor can increase to about 3 to 4% when the load reach 1 or 1.5 kilogram per cubic meter per day. Another information is if you compare the emission factor during the winter period for low temperature or the summer period with high temperature, for the simulation or for the observations, you can see lower emission when the temperature is high, so at the end of the summer. And this is something which is now observed in different systems in international publications. And what we can say in our simulation is we can explain maybe this difference is not only by the nitrification, but also by some of the denitrification of the N₂O, which is encouraged when the temperature increases and when you have less oxygen diffusion. But these mechanisms are not completely understood, but you can see that we observe both on both cases this type of effect. So one of our recommendations would be to design this BAF system with applied load, which are not higher than 0.5 kilogram per cubic meter per day. Obviously, if you do that, you need more space. You have higher BAF for treating the same load. But I really encourage you to compare the emission factors and the greenhouse gas emission and the climate change impact with LCA. When you increase the emission factor of N₂O by 1 or 2% to the infrastructure impact. And clearly, most of the studies indicate that when you increase by 1 or 2% the emission factor for N₂O, the climate change impact is much higher than the background impacts of the constructions. So I guess it's probably preferable to increase the size of the installation to reduce the emission factors during the operation. Well, that was for the design criteria. And if we move now to the question of control, for such kind of system, when you nitrify in biofilters, the aeration can be one control question. How can we change the aeration control to decrease these emissions? Another topic is the recirculations. If you do, for example, pre-denitrification. So on the upper part, you can see what we obtain with simulation when we compare feedback, feed-forward, or mixing feedback and feed-forward system for controlling the aeration with ammonia measurement in the outlet, in the inlet. On the right side, what you can see is the difference in terms of N₂O emissions are not that significant, except if you use not only the aeration, but also the recirculation in order to control that emission. You still see this emission factor, which is proportional to the load, and it's very difficult to obtain a control of aeration, which significantly decreases this emission factor. On the bottom, you can see what we can obtain if we control also the recirculations. And what we observe with simulation is that we expect much more effect on the emission factor for two reasons. The first is when you recirculate the wastewater from the nitrifying system to the pre-denitrification, a part of the N₂O produced by nitrification will be denitrified in the pre-denitrification system. And another explanation is also the fact that you dilute the nitrogen concentration when you make this recirculation. And this can be obtained either by internal recirculation with or without pre-denitrification. So on the right, you can see a decrease of the emission factor, which is proportional to the recirculating ratio. When you recirculate from 100 to 300% of the flow, you can decrease quite significantly the emission factor. So that's also something which needs to be demonstrated in practice now, because it's only done with simulation. Okay, so if I move to the last take-home messages. So as Alem presented before, what we can say about the other source of emission, we still need to have more data and more research on the N₂O emission from sewage sludge systems. That's one message. And on the other hand, the emission from in the receiving waters were clarified and now can be used for the ASTI emission calculations for the French site. And if I conclude by global outlooks, well, and what are the next steps? Well, first we want to continue to obtain data on the sludge as I said, but also on BNR processes, probably on other activated sludge systems. It could be interesting to see in some system for which the load are higher or the operating condition are different, but also for IFAS, BAF, and granular sludge system also. For the analysis, what we want to do is to start to have a campaign with N₂O sensors, which are installed continuously on the treatment plant. So at the moment, we don't have this type of data, but we have at least 2 or 3 sites in which this system are continuously installed, and now we are waiting for analyzing this new data, and I think we'll have more information if we have continuous measurement during all the year. And obviously, we want to adopt this information of, we have a national inventory. We will probably communicate on that, and we can also say that we need more information on the emission factor, but also about the activity and the performance of the system to do the analysis that Romain presented before. And at the end, I hope these activities will help the ASTI to develop some strategies for the water sector decarbonization scenarios for 2015, including the N₂O emissions. Thank you very much.
Thank you, Mathieu, and thank you for all the presenters for these contributions. Now, if you agree with that, we'll move into the discussion session to address some of the questions. So if Alam, you would turn on your camera, I think this part we can just openly discuss the questions that came up. Many of those were about the monitoring. So for example, how would you assess these in like monitoring campaigns or continuously monitoring? How do you set up the models based on shorter campaigns? Because we know that N₂O has like a very high seasonability, so it would be difficult to determine if you are just starting up with your N₂O journey. So can you comment on from the research side to the practical side, and even on the downstream receiving water and the sludge side? So many questions on this measurement topic. Who wants to start?
Alem probably can start, I think.
Okay. What I can say is that indeed in our data set, we had different monitoring times that ranged from few days, I would say, to several weeks for activated sludge systems. And in general, measurements were conducted at different periods, like summer versus winter, to assess variability related to temperature and also changes in loading conditions. For BAF systems, we had much longer monitoring campaigns that were extending up to several months. But what we have seen is that in all our activated sludge systems that we monitored, they were designed to achieve full nitrogen removal. So nitrification and denitrification were quite stable, I would say, over the course of the year. And this is thanks to the overloading or the fact that they were working with, underloading, sorry. So nitrification was, and denitrification was quite stable. And if we look at data that were collected in winter versus summer, no big difference. The emission factors that were collected by different teams with different protocols in different plants were overall low in activated sludge systems. And obviously this seasonal variability is of course true in activated sludge or wastewater treatment bioprocesses, but also true when you look at N₂O emissions in receiving water bodies. So as I mentioned it, we had data that were collected over several years there in winter, summer, different seasons. So here we have a mix of different environmental conditions. And the same applies, of course, for sludge management.
Okay, just a quick question before an input from our other panelists. These measurements are based on the liquid, like the dissolved N₂O, right? In every case, or sometimes you are measuring off gas? And if yes, how do you define the location of the off gas measurement?
Was the question about receiving water bodies or wastewater treatment processes?
All. Any information that you can share? Yes. I mean,
Okay.
I assume that with the sludge, it's more complicated. So like the spreaded sludge and as you mentioned before, the incineration, it's more straightforward to measure. But when you spread out the sludge, it's quite more, make it more complicated. But
so,
yeah.
Maybe I can answer and then let maybe Mathieu and
the others.
complete. So in wastewater treatment processes, it was mainly, N₂O emissions were mainly estimated using the off-gas method, so collecting the off-gas and directly measuring the gas. But in many cases, dissolved N₂O sensors were also used. In the receiving water bodies, as I mentioned it, N₂O were measured, dissolved N₂O was measured in the bulk water. And the emission factor is not really an emission factor, but more like a proxy of an emission factor, because it's estimated from the ratio between dissolved N₂O in the water and nitrate concentration in the water.
Yes, okay, thank you.
But yeah, most of the study, I mean, the common feature was off-gas measurement in all the data we collected from France, at least. Internationally can be a bit different, but in France, we all had at minimum the off-gas measurement, either through the hood system, or we had plants which were fully covered, could provide a temporary cover of a bath, for example. It's much simpler to cover something which is 100 square meter or 50 square meter than a full activated sludge plant. So in some of the bath system, it's fully covered, so it's much easier to collect. Sometimes with a hood, but each time the protocol was checked with us to make sure we could incorporate that data into the mix, knowing that there was a proper protocol to put the hood and at few locations to make sure it's representative of the. So all that approach, I think, by all the different entities performing the N₂O was relatively well followed, and we checked that. But it's true that when you do that, if you can put N₂O liquid sensor at the same time, it's very valuable information. If you can leave the N₂O liquid forever, it's great, but then it's a question of maintenance, investment. It is the same story, everywhere in the world. It's when it's, as long as it's not part of the local regulation, it's a bit difficult sometimes to force or to enforce that as a, that everyone put an N₂O sensor in their plant. But we might come to that situation, and we will get much more valuable information if that happened one day, for sure.
Mm-hmm.
If I can add a word about measurements, well, for the best campaign, I would say we have both the liquid measurement and the wood or the gas measurement. And if I remember well, for the biofilters, for instance, about 25% of the N₂O were coming out from the liquid phase and 75% in the gas phase, in the air. So it can be an answer for one question I've seen in the QA related to the fact that what happens if we can treat the gas for the plant which are completely covered. So clearly, most of the emissions in our case were observed in the gas phase and not in the liquid But also you can also consider that in the liquid phase, if you go into a denitrification step, after the nitrification, this dissolved N₂O can be also removed by the denitrification. So at the end, yeah, you have two challenges to manage the liquid N₂O, the dissolved N₂O, and the gas one. And in the future campaign, when we want to continuously measure the N₂O, what I've seen is that people like the liquid sensors, probably because they are easier to maintain, to manage. And we have tried to see if we can make correlation specific for each systems in order to estimate the emission in the atmosphere, in the gas, only by measuring the soluble N₂O. But this need to be well calibrated for each systems, depending on the season, on the temperature, and many things. And after that, maybe we can implement some automatic control system by measuring the soluble N₂O continuously, and maybe not necessarily the gas one, but that for future perspective, obviously, just ideas.
And just maybe to add on that, one of the issues we had with the N₂O sensors is the quantification limit, because in activated sludge, N₂O emissions are that low that dissolved N₂O concentration was not actually measured by the sensor. It was like the atmospheric one we have in equilibrium in water. So indeed, dissolved N₂O quantification is interesting when you're working with quite high emitters. Otherwise, it's really complicated to measure something accurately, I would say.
Yes. Okay, thank you. Actually, in our audience, there are quite some people who do have closed and covered wastewater treatment plant, even conventional activated sludge. So that is a question that is of high interest, I think, especially in the Nordic countries. I'm not completely sure about that. So yes, this gas capture and air treatment can influence the overall emission factors. But I think that when you talk about emission factors, it is still emitted, just treated afterwards, right? So in the case of a covered facility, you have the same emission factors essentially, but the gas is covered, doesn't go to the atmosphere, and therefore it can be treated. Or you would consider
when you have
separate.
it's true, when you have a cover plant, you could imagine then to channel the off gas. I mean, the off gas needs to go somewhere. So, but what we've done a quite intensive measurement on conventional odor treatment, and clearly it doesn't give any significant N₂O measurement. Like if you have an off gas plant and this off gas goes to chemical scrubber or those kind of system, which is usually used on plants, it doesn't give you any N₂O credit for free, I would say, because you look at other compound, but you don't get really N₂O removal. We know that there is some possibility to treat N₂O if you have captured the off gas before releasing that into atmosphere. Catalytic system are one way and so on. They are heavy to put in place, but it is a possibility. Some people are working on it. And it could be an answer in some cases also, but it will come at a cost. But this, when your plant is covered, it's a possibility that you can have. It's to destroy or remove the N₂O one way or another. But it's not going to be done magically by your other treatment plant already in place in your system. It needs to be something else.
Okay, thank you. So in the Q&A part, Mika just shared a little document on the off-gas treatment, if someone is interested in the Nordic experience. And just one quick question for the end. Would you consider utilizing the N₂O measurement as a variable describing the efficiency of the biological treatment in the wastewater treatment plants. In short, can we in the future utilize nitrous oxide emissions to optimize controls, aeration control, recycles, etc.? I see our audience N₂O as an inefficiency in a biological pathway that we can optimize on. Thank you for the question. So a quick input before we close up today's session on this, whether N₂O can be considered in the future like an indicator of the plant efficiency, in your opinions?
Well, I would say yes. From our first simulation using this type of measurement, we can say yes, but obviously you need to define what are the criteria for defining the performance of the system. So because now if we want to optimize simultaneously the removal performance and the emissions of N₂O, mitigation of greenhouse gas, it means that you need to develop controllers with multi-objective optimization. And this can work, but obviously when you use these N₂O sensors to aerate, to control the aeration or to control the recirculation, as I have shown, it will change also the performance for nitrogen removal and denitrification, etc. So you need to define some kind of laws to balance between different kind of objectives at the same time.
Yes, exactly.
And I think it's saying that a plant which doesn't emit N₂O is obviously a healthy plant or well-operated plant. And it's probably, we can say it's probably a true indicator for activated sludge. But again, it depends what you want to do. And we see for biofilter, for an amok system, when we have the first nitration stage, we produce nitrine and so on, some pathway we want to achieve because there is a clear benefit to do that, will generate by essence or by nature or by the mechanism involved more N₂O than something which is activated sludge with BNR, one-to-one, the basic system. So it really depends on what you want to achieve. And therefore, I don't think we can say it's always linked to the good behavior or good operation, because in some operation you are targeting, it might generate some N₂O by nature, I would say. And therefore, it's more a question of where do you put the balance between cost, chemicals, electricity, N₂O reglementation, your carbon footprint. So you have to have a multi-criteria decision to see where do you put the cursor. But it's true that if you want to control, liquid N₂O is clearly an additional thing you can put in your controller. We have ammonia, we have online phosphate, we have DO. We can have sometime control based on energy requirement and price on energy on the grid. And so all that can become one of the story. You need to, what is your driver locally in your plan, what you want to achieve, but it's clearly a possibility.
Yes, I think this is exactly what they do right here in REN. Alam, final thought maybe? All right.
No, I think Romain and Mathieu already well covered this question.
Okay. Thank you, Dan. So as our time has come to an end very quickly, on behalf of the Climate Smart Utilities team, I would like to thank our presenters, Alam, Romain, and Mathieu, as well as the entire ASTI Greenhouse Gas Working Group for their contribution to this field and for sharing their work with us. You may also have seen them in the chat. As well as the International Water Association team for their help and support of this webinar. And of course, you, dear listener, for your interest and active participation. We had some very interesting questions, and I hope that you found this webinar insightful. And if you did, why not sign up here in this QR code or in the link in the chat box. You will receive information about the activities of the group. And before you leave, I would like to recommend a couple of upcoming webinars and events in these next slides. There is a webinar next week on the advanced oxidation processes, and another one at the end of May on introducing AWS, some upcoming conferences in Houston, Texas, the Leading Edge Conference in the beginning of June, and also the World Water Congress, where climate smart utilities will be also present. It will be in October. Registration are all open. And if you are, also the Digital Water Summit, I almost forget about this. And if you would like to join the International Water Association, there is a little discount that you can use for this webinar. And with that, I would like to thank you for your attention, and we are a few minutes after the time, but I hope that everybody enjoyed. Thank you so much for the discussion, dear panelists. I think it was very interesting, and I'm looking forward to the next updates on this, because I saw that you will have a working group on methane, which would be very interesting for us because we are greenhouse gas emissions group, but we mainly focus on N₂O. So will be nice to also focus a little bit on methane. And
thank you, everyone, and thanks for this opportunity. Bye bye.
Thanks.
Bye bye. Thank you.